Alright, so I'm in the middle of proving all these things about integrals. I had to hurry last time because my 5 minutes were up, but the integral of kf, go through, you get k times infimum, which equals k times u of f, which equals k times the integral of f. So we're done. So what I'm going to do now is I'm just going to select, just going to erase all this, and then we're going to get on to the third proof. So the third proof, and I'm only going to do half of this because it's very similar. Proof 3, I like working with the u's rather than the l's. You may have noticed this. So I'm going to assume that f is less than or equal to some capital M. This might be the supremum of f. It might be just some gigantic number. I'm going to prove that the integral of f is less than m times b minus a. Well, once again, you just kind of follow your nose. The integral of f is defined to be, again, I like the u's. You could do these with l's, and maybe you should, which equals the limit, or not the limit, the infimum of the set of u of f of p's. You want to get to the u of f of p's because these are just finite sums. These are just add up areas of rectangles, which is really pretty easy to deal with, which equals the infimum of the sum of the mi times xi minus 1. Should be using delta x probably. That'd be a lot faster. Well, this is the supremum of f in the interval. But the supremum of f is going to be less than or equal to m. M is an upper bound, so it's got to be less than or equal to the supremum in each interval. So I can replace this with the infimum of the sum of not mi, but just plain old m over p. Oh, but by definition, this is the infimum of, I'm going to sum over p, the u of m, the constant function m. So here's the function m. That's just, right, if the value is always m, that's going to be an upper bound. So this is just u of m of p, which equals u of m, which equals the integral from a to b of m, which equals m times b minus a. And so we get this half inequality. Integral of f is, this should be less than or equal right here. Integral of f is less than or equal to m times b minus a. And the other half is very similar. All right, we're almost done. So proof 4. So I'm going to assume that f is less than g, and I'm going to let h equal to g minus f. And if you do this, right, I know that f is less than or equal to g, so 0 is less than or equal to g minus f equals h. So I get that h is always less than or equal to 0. So by 3, with little m equal to 0, so I'm just using this up here with little m equal to 0 and an h right there, 0 less than or equal to h implies 0 times b minus a, 0 equals 0, b minus a is less than or equal to the integral of h. But the integral of h equals the integral of g minus f, which is equal to, by 1, integral of g minus the integral of f. So 0 is less than or equal to integral of g minus the integral of f, and I can just add the integral of f to both sides to get integral of f is less than or equal to integral of g, which is exactly what I need. And then finally, by proof 5, I get immediately by f is less than or equal to the absolute value of f. By 4, integral of f is less than or equal to the integral of absolute value of f. And here you just need to prove that f is integrable, which is an exercise that you're told to do earlier. So that's the proof of these are how the proofs goes. You largely just unravel by following your nose. Figure out, okay, integral of f, what's that defined to be? That. Okay, what's that defined to be? That. What's that defined to be? So that's all there is to it. Bye-bye.